Opposing reactions. These are also called the reversible reactions, and these are the reactions in which the products of the chemical change they react together to form the original reactants, and these are called the opposing or the reversible reactions. These reactions do not proceed to completion because there is always an opposing reaction taking place. So they do not go to completion, and the equilibrium state is achieved when the rate of the forward reaction and the rate of backward reaction both are equal. Kinetics of the opposing reactions. For the case when the forward and the backward reactions both are of the first order, then if we take a general reaction like A gives B, the rate constant for the forward reaction is K1 and rate constant for the backward reaction is K2. And these are the conditions, means initially when T is equal to 0. Concentration of A is small a and concentration of B is 0 because B is not formed initially. And at time T, the amount of product formed is X and the concentration of reactant is A minus X. And at the equilibrium condition, the concentration of product is Xc and the concentration of reactant is A minus Xc. Now, if K1 is the rate constant for the forward reaction and K2 is the rate constant for the backward reaction, the rate of forward reaction is given by K1 into A minus X, and the rate of backward reaction is given by K2 into X. Net rate of the formation of B, that is the product at time T, is given by forward rate minus the backward rate, that is dx over dt. dx over dt is equal to k into a minus x, k1 into a minus x minus k2 into x. This is equation number 1. At equilibrium, when x is equal to xc and dx by dt is equal to 0, then our equation becomes k1 into a minus xc minus k2 into xc, that is equal to 0 at the equilibrium concentration, or k1 into a minus xc is equal to k2 xc, or the k2 is equal to k1 into a minus xc divided by xc. So this is the value of k2, that is k2 is equal to k1 into a minus xc divided by xc. This is equation number 3. Now from equations 1 and 3, we get that dx by dt is equal to k1 into a minus x minus k1 into a minus xc by xc. Here we are replacing k2 by its value from equation number 3. So this is the equation for the rate of reaction. Now that is equal to, if we take k1 as common, k1 into a1 xc minus x xc minus ax plus x xc divided by xc. So this cancels out, x into xc and minus x into xc, they get cancelled out, and what we get, dx by dt is equal to k1 into a into xc minus x divided by xe. Now collecting the terms and integrating, what we get, integral of dx over xc minus x is equal to k1a by xc integral dt plus c. This is the integration constant. So after integration, we get minus ln natural log of xc minus x is equal to k1a into t by xc plus c. This is equation number 4. By putting the initial conditions, that is at t is equal to 0, x is equal to 0, minus ln xc is equal to c. If we put here x is equal to 0 and t is equal to 0, this equation number 4 reduces to equation number 5, and we get that minus ln xc is equal to c. We are getting the value of the rate constant. From equations 4 and 5, what we get minus ln xc minus x is equal to a1 at by xc minus ln xc. What we are doing, we are putting the value of integration constant in the equation number 4. So by solving this, what we get minus ln xc minus x plus ln xc is equal to a1 at by xc, and solving again afterwards we are getting ln xc upon xc minus x is equal to k1 at by xc. So k1 is equal to xc divided by at into ln xc upon xc minus x. K1 is equal to 2.303 xc by at. We are replacing ln by the natural by log with base 10 here. Log of xc divided by xc minus x, and from equation number 2 we get that a k1 minus xc k1 is equal to a2 xc. So a k1 is equal to xc into k1 plus k2. Now k1 plus k2 is equal to a k1 by xc. So from 6 and 7, what we get, we are getting the value of a1 in equation number 6, and k1 plus k2 is equal to so much from equation number 7. So from k1, from 6 and 7, what we get, k1 plus k2, here it is a k1 by xc. So k1 is what? K1 is coming from the equation number 6. Putting it here, what we get, that k1 plus k2 is equal to 2.303 by t log xc upon xc minus x. If kx and xc and the t values are known, then k2 can be calculated. Now, what are the examples of the opposing reactions? NH4CnO gives CONH2 twice. Rate constant for the forward reaction is K1, and for backward reaction it is K2. So example of opposing reaction. One of the opposing reactions is alpha D glucose gives beta D glucose, where rate constant for the forward reaction is K1, and for backward reaction it is K2. So these are the two reactions which are the examples of the opposing reactions. Now we will study about the parallel reactions. These are the reactions in which a substance reacts or decomposes in more than one ways. Means it is forming, A is forming B also, and A is forming C also. So it is decomposing in more than one ways, and these are called parallel or side reactions. So the rate constants for these reactions are, side reactions are different. One is called the main reaction and the other is called the others are called the side reactions. If one reaction utilizes the major part of the reactants, it is called the main reaction. Main reaction, that reaction is called the main reaction, and the other reactions are called the side reactions. For example, when ethyl alcohol is made to react under different conditions, uh, it is given by this reaction here, is shown here, that C2H5OH gives C2H4 plus H2. Again it is giving C2H5OH is again giving CH3CHO plus H2, and it is giving C2H5O C2H5 plus H2. Means it is alkane, aldehyde, and the ether. They are all formed from ethanol, and the rate constants are different for each and every reaction. For first reaction it is K1, for second it is K2, and for third it is K3. So the reaction which is utilizing the major part of the reactant, that is the main reaction, means this is the ethane formation. C2H4 plus H2O is called the main reaction, and these other two are called the side reactions. Now, kinetics of the side reactions. For the reaction A gives B and A gives C, having rate constants K1 and K2 respectively. If A is the initial concentration of capital A, means reactant, and X is the amount of A reacted in time T, then what is A minus X? It is the amount of A left unreacted after time T. The rate of formation of B is equal to K1 into A minus X, and the rate of formation of C is equal to K2 into A minus X. So the overall rate of reaction is equal to K1 into A minus X plus K2 into A minus X. Means adding both the rates, we are getting the overall rate of the reaction. Now dx by dt is equal to K1 into A minus X plus K2 into A minus X is equal to K1 plus K2, taking K1 and K2 here, and because A minus X is common in both these terms, you can take it like, write it like this, that is equal to K1 plus K2 into A minus X. This is equation number 3. Now integrating equation number 3, what we get? Integral dx upon A minus X is equal to integral K1 plus K2 dt. So this is equal to minus ln A minus X is equal to K1 plus K2t plus C. We are putting initial conditions for knowing the integration constant. What we are doing, we are putting the initial conditions, that is at t is equal to 0, x is equal to 0. So putting in this equation, what we get, minus ln A is equal to C. So minus ln A minus X is equal to K1 plus K2t plus C. In this equation, we are putting the value of C. Minus ln A, so ln, taking this minus ln A to the left side, and then ln A upon A minus X is equal to K1 plus K2 into T. That is K1 plus K2 is equal to 1 upon T into ln A upon A minus X. Now we'll study the consecutive reactions. Consecutive reactions are the reactions in which proceed from the reactants to the final products through one or more intermediate stages. Means there is not a single step. There are many steps. Means A is forming B, B is forming C, and so on. The overall reaction is a result of the several successive steps. Means one after the other, one after one after one, the other. These steps are taking place, and we are getting B from A and then C from B, having rate constants K1, K2, and so on. So every step of the reaction has its own reaction rate and velocity constant. For example, H2O2 gives H2O plus O. This is slow reaction. And then O plus O gives O2 is the consecutive. These are the successive steps which are taking place. And this is the example of consecutive reaction. Other example is CH3 twice CO is equal to CH4 plus CH2 double bond CO. And the second step is after the formation of CH2 double bond CO, it is again forming half C2H4 plus CO. So these are the successive steps of the same reaction, and finally the product is C2H4 plus CO. Now, kinetics of the consecutive reactions. In general, A gives B and B gives C. If the rate constants are K1 and K2, then we can write the initial conditions as concentration of capital A as small a. B is 0 and C is 0 initially. After time t, capital A means reactant concentration is X, and the intermediate concentration Y, and concentration of C is Z. So the rate of disappearance of A is equal to minus dx over dt is equal to k1x, or minus dx by x is equal to k1 dt. Then Collecting the terms and integrating, what we are getting, minus dx over x is equal to k1 into integral dt. So minus ln x is equal to k1t plus c. Now put the initial conditions at t is equal to 0, x is a. So minus ln a is equal to 0 plus c, and c is equal to minus ln a. So we are getting the value of the integration constant. Putting it in the equation, what we get, ln a minus ln x is equal to k1t, or ln x minus ln a is equal to minus k1t, or ln x by a is equal to k1t minus k1t, and x by a is equal to e to the power minus k1t. So x is equal to a into e to the power minus k1t. This is the expression for x, and here it shows that the concentration of a falls off exponentially with time.